Let's look at in Engineer how to represent an AC signal. For example, we want to express a AC voltage. We use small letter V, and then this is a function of T. Next, this is the maximum, the amplitude of the signal. Here I put 20. Now if I don't write the unit, it will be assumed as volt. Next, we can put a sinusoidal function. Now remember, the signal doesn't have to be sinusoidal. It can be a triangular, it can be like a square wave, but sinusoidal is the most common way. And also there's another more advanced theory, say you can break down any periodic function with a series of sine or cosine function. Cosine is the one we usually use, so we use cosine instead of sine. Now this we call the argument of the function. This argument of function suppose a theta, the angle. Now this angle will change. Now how this angle change? We can say, make an analogy. If a car moves along a straight line with a velocity v, and if the displacement is s, so we can write the displacement equal to velocity times time, and displacement is measured by meter. This is in second, so the velocity is meter per second. Let's look at the case. At time equal to 0, there's a vector with 1 unit of length is along the x-axis, and this vector start rotate, and after some time of t, this vector rotates to this angle, this position here. So the angle here is theta, and this theta change with respect to time. So we can write theta equal to the velocity. Therefore we call the angular velocity because it's the change in angle multiplied time. And theta is measured in radian. Incidentally, radian is just like a reminder. Radian itself is not really a unit. It just reminds you this is a number. It tells you about the angle. And if you look at how the radian is defined, you will see it's the arc over the radius. So the length over length, there's a dimensionless. So you can always drop radian, and some people don't even write radian. You just say a number. So here, time measure in second. So this one we can say is radian per second, or just say per second is good enough. So we can say omega play the same role as velocity in linear motion. V as a function of t, the maximum value 20, cosine instead of theta or an angle we write as omega t. When you project this function along the axis, along the x-axis, this length here, this is cosine omega t or cosine theta. Another thing is omega also can be interpreted as called angular frequency. So let's think about what I mean frequency. If this vector rotates 2 rotations in 1 second, so we can say the frequency F is 2 rotations per second. And also we can say this is 2 Hertz. Now we can ask the total angle it rotates in 1 second, because each second it rotates 2 rotations. So In 1 second, it rotates 2 multiply 2 pi. And this is our angular velocity. So angular velocity can be written as 2, this is the frequency, each second how many rotations, multiply in each rotation, it is 2 pi of radian. You can write as 2 pi f frequency. So our important relationship is omega equal to 2 pi frequency, because f is the frequency, just counting how many rotations, and we call omega angular frequency. Now let's answer this question now. If we compare 100 pi t with omega t, so omega is equal to 100 pi. This is per second, and omega is equal to 2 pi f. So if we compare here, we can write 100 pi as 2 pi multiply 50. So f must be equal to 50 hertz. Period frequency is in each second how many rotations, and period is each rotation how long it take. So for example, if I say each second it rotate 2 rotations, so f equal to 2 hertz. So it means each second 2 rotations, and each rotation will take half the second. So period is 1 over f. So it's measured by second. So this is 1 over f, and this is 1 over 50, and this is 0.02 second. Angular frequency omega is equal to 2 pi frequency. So f is equal to omega over 2 pi, and this is 200 pi over 2 pi. So it is equal to 100 hertz. And period is equal to 1 over frequency, and 1 over 100 second equal to 0.01 second. Let's consider this example. I have a triangular function here, and this is 1, minus 1, and 1. Now I can write the triangular function as f(x). The important point is that when x equal to 0, this is a peak. It means f(x) equal to 1. Now, if instead of f(x), if I write f(x minus 5), what it means? It means when x equal to 5, the f5 minus 5 is f0. It means as if the original function at x equal to 0. So what I mean is we shift this triangular function to the right 5 unit. So we can shift this one here, and this is 5. So you can see in general, if we have a function f(x), and if we want to shift the function to the right hand side of the x-axis by x0, so I can write this one as f(x minus x0. This is how we shift a function to the right hand side. Now similarly, if we want to shift the function to the left hand side, say to the -5, so this function can be written as f(x plus 5). So the sign here plus means shift to the left hand side. Why? Because this time when x equal to minus 5, this function now become f minus 5 plus 5. It means f0. So the same, which is the peak, the maximum at f0. So this is how we interpret it. So again, fx plus x naught. This is general. Negative means to the right. Positive means to the left. If this axis represents time, it means so-called the time domain. We have similar interpretation. So f as a function of t, if now you put t minus t naught, you shift your function to the timeline to the right hand side. And if you shift here t minus t naught, you shift this function to on the timeline to the left hand side. However, because this is the time, so we have to interpret it. This one is slightly different. It's not the space. If what happened is, for example, this triangular function at time equal to 0, it is 1. It means this is the peak. Now, what it means is, if you shift this function to 5 seconds, so it means ft minus 5. So what it means now, when t equal to 5 seconds, this is 5 minus 5 is f0, so this is peak. It means equal to 1. So we can interpret this before you have a function, and this function at time equal to 0, it reached the peak. Now you have another function which is written as f bracket t minus 5. It means this function. So if this is the t, this function reached the peak at time equal to 5 seconds. So this happened later. Or we say f t minus 5 is lag compared with the original function here. Now the same argument, if you put this function f t plus 5, so what I mean is, when t equal to negative 5 seconds, this function will reach the peak, unit 1. But what I mean negative 5 seconds, it means just mean before we start the clock, and assume this already happening. It just, you can choose when to start your clock. So it means when we write the function f bracket t plus 5, this function here is happen before the original function. So we can say this function lead the original function. So again, we can now interpret it slightly different. In the time domain, if you, instead of ft, you write ft minus t naught. The second function here is lag compared with the original function. It happened later. If you write this one as t plus t naught, this function here happens before the original function. So this is lead the original function. So this is the idea of how to compare the two functions. Now let's look at the cosine function here. V1 is tan cosine omega t, and V2 is tan cosine. Now in the argument, instead of omega t, this is negative 30 degree. Now this is a catch here. It's very important. When you write V1 equal to 10 cosine omega t, as we discussed before, omega t, it is a number. It is an angle measured in radian. And this has to be this, because this is how the angle change with respect to time. So it must be in omega t, and this has to be in radian. Now, in physics and mathematics, there's a rule. All the variables must have the same unit. So you will say, if you want to express a shift of the function, or this function happened earlier or later, you must also express angle omega t minus another angle, and this angle must equal to or written in radian. However, in engineering, it's very difficult to think of radian. Say, it's difficult to think of 0.25 pi. It's very difficult mentally to imagine how much is this angle. We still a lot easier to imagine, say, 45 degree, 30 degree, 60 degree. So engineering have a convention. This angle here, instead of written in radian, they write in degree. So we have a situation now. We mixed the unit in the same expression. Remember, this in physics and mathematics is a big no-no. You're not supposed to do it, but in engineering, you can do it. So 30 degree means now we shift this function to the right hand side 30 degree. And in terms of meaning, it means this function here, as we discussed before, is happen after this function. So I will say V1 lead. So in terms of plot, we can sketch this one. V1 is a cosine function like this. Now this is time t, but we can still see this one. If we think this as a angle, this is 2 pi, or this is a 360 degree. So think in angle, we shift another function to the right hand side. So how many degree? 30 degree. So it means this one 30 degree. This is another function. So the wet one is V2 10 cosine omega t minus 30 degree. If you really want to know the time difference between V1 and V2, you mean this delta t here, this time you have to convert, say, 30 degree over 360, okay, and convert this one back to 2 pi. So this is the angle in radian. So after you convert this one, if you write this one in omega delta t, so if you know the omega, you can calculate delta t, and this will be the exact time, how much time is shift, or how the time it happened later. The voltage is V maximum cosine omega t. And remember, this omega t, this angle is in radian. The current is I maximum cosine omega t plus 90 degree. Again, this is in radian, but in engineer, it is allowed to write this angle in degree. Now we call this one phase angle. It tells you how much which function appear earlier or which function appear later. So we'll say the phase angle is 90 degrees. Remember, this is positive 90. As we discussed before, it means the current shift to the left hand side in the time domain. It means the current happened before the voltage. If you plot the voltage and current on the same graph, so this is time domain, so the horizontal axis is time, and voltage is a cosine function. Now the current shift positive 90 degrees. If you think in terms of phase or in terms of angle, this is 90 degrees. So it is maximum here. So this one here, this one here. Okay, so this is positive 90 degrees. So what I mean is the current leads the voltage, or you can say the voltage lag behind the current. A lot of time we only interested in the phase relationship between signals. So instead of plotting all signals along the timeline or the time domain, we can just represent signals as vectors. First consider 20 cosine omega t. We'll put this signal, this voltage, along the horizontal axis. So this by default is cosine omega t, a function along the horizontal axis. Now if we have another function 20 cosine omega t, but this time in terms of time domain is shift to the left hand side plus 60 degrees, or this function, the second function here, actually lead the original function. On the phasor, we use vector again. Incidentally, the length of the vector is the amplitude, so we will say this is 20 units. Now we can draw another vector which is 60 degrees. So this is the amplitude, and this represent 20 cosine omega t plus 60 degrees, and this is our phase angle, and this angle is positive, so we rotate this vector anti-clockwise. Remember, in science and engineer, we always rotate a number and angle anti-clockwise, means positive. Instead of writing this one in time domain, we'll write this one just the amplitude and the phase angle. So this angle positive 60 degrees. So this is the way to write the function or the signal in the phasor form. It only focuses on the amplitude and the phase angle, and you should supplementary what is the frequency. We can also think this one like a complex plane. So this is a wheel axis, and this is the imaginary axis. In engineer, we use J instead of I for the imaginary number. So now our problem becomes how to represent this as a imaginary number. An imaginary number, there's a two form to write. We can write this one in rectangular form. It means we want to project this one along here and along here. So 20 cosine 60 degree, this is your wheel component, plus J 20 sine 60 degree, this is the imaginary component. The magnitude of V1 is 10 volts and the phase angle is positive 30 degree. So this is roughly about right V1. And the magnitude of V2 is 10 volts, but the phase angle is negative 45 degree. So this is V2, and this is 30 degree, and this is 45 degree. So the phase difference between V1 and V2 is 75 degree. So we can say V1 leads V2 by 75 degree, or alternative, we can say V2 lag behind V1 by 75 degree. This complex number is expressed in rectangular form. To find the polar form, we first find the magnitude of this number. So let's plot this number on the complex plane. This is the number here, and this is 3 plus J4. The polar form is represented by the magnitude of this complex number and the angle here. So we can say easily now the magnitude, what we call the Z, the magnitude or the absolute value is equal to 3 square plus 4 square square root, and this is 5. Tangent theta equal to 4 over 3. So the angle theta equals to 53.1 degree. So this complex number can be expressed as 5 angle 53.1 degree. Like a polar form, it means focus on the magnitude and the angle. Another way to write this one is to write it as 5 exponential J, and this angle is 53.1 degree. If we connect a AC signal in series of a resistor and an inductor, we have a RL circuit. Now, because these two components are connected in series, so the current at each point I here and I here, of course they will change direction. They are exactly the same. If I measure the voltage across R and also measure the voltage across the inductor L, that's what we will find. Let's express this quantity on the complex plane or on the phasor. So we put the I along the x-axis. On the resistor, the I and the voltage, they're in phase. What it means, if we plot I and voltage, peak match the peak, trough match the trough. So they're in phase. Now we can put this one represent the voltage. Ohm's law will work. So we can say VR is proportional to I, and this is the R here. This V here we can understand as the peak. It means the maximum, and this is the maximum. However, we can also divide this by root 2, root 2. It means we can also write this one in root mean square value, root mean square value, as long as they are consistent. Now we compare the voltage across L. What we find is the voltage across L is actually lit 90 degrees. So this will be VL. The magnitude of VL, the voltage across the inductor, is proportional to the magnitude of I. This proportional constant, if we go into the theory, is equal to omega L. It means this is similar with VR, the voltage across the resistor, equal to RI. So you can interpret omega L as if our R, but this time, because we have a factor of omega, when omega increase, it means the frequency increase, the omega L also increase. Omega L play the same role as resistance in Ohm's law, so this also measured in ohm. We have to express or tell people VL is 90 degrees ahead of I. So how to express? Therefore, we write this one as J. Now we rewrite everything. We'll say VL is equal to J. It just means it's lit the current. So in the phasor, it's 90 degrees ahead. So J omega L I. And we put this one, we call this one complex impedance for inductor. So in our expression here, we can plot this one on the plane. Remember, R is along the x-axis or the wheel axis, because R is proportional to I and VR. So this is R, and the XL, the impedance for inductor, is 90 degrees lit. So I will put the inductor here, and this is XL. Therefore, you can see this is how we express Z equal to R plus JX. So this is our Z, and this one is called the phase angle. Now, what this phase angle mean is, in this circuit, if look at here, the V, actually the input of the V is V maximum cosine omega t plus theta. So the phase angle of the input is here along the Z, the complex impedance, and the phase angle, the voltage across the resistor is Vm cosine omega t, and here the voltage across the inductor VL is Vm. This is for the inductor, of course, and this is cosine omega t lit plus 90 degrees. So what is the angle? Of course, now it's easy. Tangent theta equal to 15/10, and the angle equals to 56.3 degrees. The magnitude of the complex impedance Z is equal to square root 10 square plus 15 square, and it's equal to 18. Remember, it's measuring in ohm. So the complex impedance can be written as 18 angle 56.3 degree. Consider an AC signal across a resistor, and if we look at the V and the I across the resistor, we'll find they're in phase. And if you look at the power, we'll find it will look like this, because negative multiply negative equal to positive. Now the power is fluctuating, so we want to find the average power. And if we do the mathematics, we'll say the average power here, P, is equal to the peak of current multiplied the peak of voltage divided by 2. Now if we split this one into two terms, I peak square root 2, V, the peak value of voltage, divided by square root 2, it means we can consider this is the DC equivalent. So what I mean is, we take the maximum value of I and divide this one by root 2, and if we assume a DC current have the same magnitude, and we assume the DC voltage equal to the maximum of your AC divided by root 2, and they will create the same average power. So we call this root mean square value. Root mean square value is the DC equivalent. So the average power in terms of root mean square value, it can be written as I root mean square value multiply V root mean square value, or just analogy, I root mean square value square R. And of course we can express the root mean square value as the maximum over root 2 square R, or I maximum square R divided by 2. The root mean square voltage is equal to the maximum value of the voltage divided by root 2. So it is 100 divided by root 2, and is equal to 70.7 volt. The average power is defined as root mean square value of the voltage multiplied the root mean square of current. However, we can apply the Ohm's law, and we can rewrite this one as root mean square R multiply R, or root mean square voltage square divided by R. So we use this form, and this is 70.7 square and divided by 10 and you will get 500 watt. For the RC circuit, the current passing through R and the voltage across the R, they are in phase and the Ohm's law apply. So this is RI. However, the voltage across the capacitor is out of phase. It is lag behind. So I will put the voltage here across the capacitor. But it also proportional to the current, even though there is a 90-degree behind the current. So we can write this one, and this is I. The proportional constant is 1 over omega c. To represent this one is 90 degree behind the current, we put the negative J here as a complex number. This is our complex impedance for capacitor. So XC is magnitude equal to 1 over omega c, or 2 pi f c. So this is 2 pi 50 times 10 times 10 to the minus 6, and this is equal to 318 ohm. On the RL circuit, again the current passing through the R and the voltage across the R, they are in phase, and the proportional constant is R. However, the voltage across the inductor, it leads the current by 90 degree. Now again, this voltage proportional to the current, even though it leads the current 90 degree. The proportional constant this time is omega L, and we put the J here to represent this one is proportional 90 degree, and we call this one XL. So the magnitude of complex impedance for the inductor is equal to omega L, and this is 2 pi frequency multiply L, 2 pi times 50 times 100 times 10 to the minus 3 Henry. So you should get 31.4 ohm.